Imagine two computers racing. One is a monster machine, able to do 1 billion tiny operations every second. The other is much slower. Now give the fast computer a clumsy plan, and give the slow computer a smarter plan. For a small job, the monster may win. But as the job grows, something strange happens. The slower computer pulls ahead. That is the first big lesson of algorithms: speed is not only inside the machine. Speed is inside the idea. Here is the plan for this first lesson. First, we will define what an algorithm is without using scary math. Then we will see why input size matters. After that, we will compare two growth shapes, n squared and n log n. Finally, we will build the mental model for the rest of this playlist. Do not ask only how fast the computer is. Ask how the work grows. An algorithm is a step-by-step plan for solving a problem. The input is what you start with, like a messy list of numbers. The output is what you want at the end, like the same numbers sorted from small to large. Code is one way to write the plan, but the algorithm is the idea underneath the code. If the plan is confused, faster code only runs the confusion faster. Planning matters because many problems have too many possible answers to check one by one. A delivery route, a sorted order, a school schedule, or a path across a map can hide the best answer among thousands or millions of choices. Brute force says, try everything. A good algorithm says, use the structure of the problem so you do not have to. Computers are fast, but not infinitely fast. Memory is cheap, but not free. So every plan spends resources, time, memory, and sometimes human attention. When we study algorithms, we study how a plan spends those resources. The question is not only, does it work? The better question is, what happens when the job becomes 10 times larger, or 1 million times larger? Sorting gives the cleanest first picture. Let n mean the number of items in the list. Some simple sorting methods do about n times n work, written as n squared. Other methods do closer to n times log n work. You do not need the formula yet. Just notice the shape, n squared eventually bends upward much faster. At scale, the shape of growth beats raw machine speed. The word log can sound heavier than it is. In this first algorithm story, think of log as the number of times you can keep cutting a problem in half. If you have 16 items, you can cut to 8, then 4, then 2, then 1. That took 4 cuts. So when an algorithm keeps splitting work in half, a log shape often appears. This is why faster hardware is not the same as a better algorithm. A faster processor usually gives you a constant boost, 2 times faster, 10 times faster, maybe more. But a better algorithm can change how the work grows. If the work explodes as the input gets larger, hardware only delays the pain. A better idea changes the future of the computation. But fast is not enough. An algorithm also has to be correct, which means it gives the right answer for every allowed input. One way to prove this is with a loop invariant. That is just a fact that stays true while a repeated step runs. If the fact is true at the beginning, remains true after each step, and gives the answer at the end, the result is not a lucky accident. When we analyze an algorithm, we usually do not count seconds. Seconds depend on hardware, programming language, and background noise. Instead, we count how the number of steps changes as the input size changes. That lets us compare ideas fairly. We are not asking whether this laptop is faster than that server. We are asking what the plan becomes as n grows. Big O notation is the shortcut language for that growth. It ignores small machine details so we can focus on the dominant pattern. Constant time means the work barely changes. Linear time grows with the list. Quadratic time grows much faster. These are not just formulas. They are survival categories. They tell us which ideas can live at scale. One of the great design ideas is divide and conquer. Split a problem into smaller problems, solve them, then combine the results. Merge sort does this with sorting. Many geometric, numeric, and search problems do something similar. The visual is a tree, one large question branches into smaller questions until the leaves are easy. In merge sort, the split phase is almost boring, cut the list in half again and again. The cleverness is in the merge. Two sorted lists can be combined by repeatedly taking the smaller front item. So instead of fighting chaos directly, the algorithm creates pockets of order, then stitches those pockets together. Data structures are the other half of the story. A data structure is a way of arranging information so future operations become cheap. A heap makes the next priority item easy to find. A hash table makes lookup feel almost instant. A balanced tree keeps order searchable. The structure is not decoration. It is stored strategy. Then comes a surprising idea: sometimes randomness makes an algorithm more reliable. Randomized quicksort, randomized hashing, and probabilistic analysis all use chance to prevent an adversarial pattern from always causing the worst case. Randomness is not confusion here. It is a shield against predictable failure. Two famous design styles feel almost opposite. Greedy algorithms make the best-looking local choice and move on. Dynamic programming remembers the answers to smaller subproblems and builds upward. Greedy is powerful when a local choice can be proven safe. Dynamic programming is powerful when the same subproblems keep reappearing. Graphs give algorithms a language for relationships. Cities connected by roads, pages connected by links, people connected by friendships, tasks connected by dependencies. Once a problem becomes nodes and edges, new tools appear: breadth-first search, depth-first search, shortest paths, spanning trees, and flows. Shortest path algorithms are beautiful because they turn uncertainty into expanding certainty. Dijkstra's algorithm, for example, keeps a frontier of possible distances and repeatedly locks in the nearest unsettled node. The map does not have to try every route. It grows a wave of known best answers. And then algorithms teach humility. Some problems have no known efficient exact solution. NP-complete problems are connected in a remarkable way: solve one efficiently, and you unlock all of them. That does not make them useless. It changes the question. Maybe we approximate. Maybe we restrict the case. Maybe we learn when perfection is too expensive. So the algorithmic way of thinking is a loop. Model the problem. Find the structure. Choose a strategy. Prove it is correct. Measure how it grows. Then improve the model. This is why algorithms are not just technical recipes. They are a way to see the hidden shape of a problem. Here is the useful mental model. An algorithm is a plan. A correct algorithm gives the right answer. An efficient algorithm uses time and memory wisely. And the growth curve tells you what happens when the problem becomes large. Once you see that curve, you stop asking only, "How fast is my computer?" You start asking, "How good is my idea?"